Hello, my name is Enrique Garcia and this is lab report number 4. As introduction, first I'm going to say the purpose, which is to observe the motion and tracker of a mass in a spring and be able to create a computational model on BPython that approximates the observed position and tracker starting from fundamental principles. Using derivations of the energy principle to understand the properties of the spring, and as a result, I obtained that using Newton's second law and the energy principle, I was able to create a computational model in which the observed motion and predicted motion were very similar. First, for the overview of the experiment, we need to understand the fundamental physics principles involved in this lab. First, those are Newton's second law, Hooke's law, and the energy principle. For the energy principle, we know that it is delta E equals delta K plus delta U, which is the change in energy equals delta K, which equals the change in kinetic energy, and delta U plus delta U, which is the change in potential energy. Second, we have Hooke's law, which is the force of the spring, Fs equals Ks times L minus Lo, which means that Ks is the constant for Hooke's law, and L minus Lo equals that position minus the relaxed position. And finally, the usual Newton's second law, which is Rf equals R initial plus F net over mass times delta T. Then, for the obtained data, we know that the item mass is 0.402 kilograms. The time step, or delta T, equals 1 over 210 seconds. The initial position I obtained from tracker is negative 0.118 in the x position, negative 0.632 in the y position. And for the Ks we obtained from the video lecture, it's 6.83 newtons over meters. The relaxed length for the spring is 0.123 meters, and the gravity equals 9.8 meters over second squared. First of all, as you can see here, we obtained a video from tracker and we analyzed all of its components. After observing the mass and making a center mass, I obtained several x and y values, which I obtained and then put in an Excel file. After obtaining those values and placing them on the first model I made on Python, this model was made to plot the y position of the movement of the spring. As you can see, the y position has a period which can start from any point, but as I choose right here, it starts in this point and it ends in this point, and this is one period of oscillation. This happens in the y position because we chose from the last slide that this was the y axis and this was the x-axis, so it always moves on the negative position of the y-axis. Then for the other model we made plotting the x-axis, as you can see, this is another period we observed which starts from here and ends here, and it moves from the negative to the positive axis. Now onto our model of BPython, we can see that I set the initial conditions over here, all of them, the other conditions obtained from the lecture, and we added K, UG, and US, which are the kinetic energy, the potential gravitational energy, and the potential spring energy. These are all values we need to calculate delta E. After doing this loop, calculating F gravity and using the Hooke's law and Newton's second law, we obtain a set of values that we can calculate, which are these that we're going to plot: T, delta K, delta US, delta UG, and delta E, which is the sum. When we run the model, we obtain this. As you can see, the movement of the blue ball also always has a black arrow pointing downwards, which is the gravitational energy, and a blue arrow pointing upwards, which is the force of the spring. Observing this graph, we can see that the energy principle is satisfied because, as you can see, when the red line is in its top, the green line is in its lowest value, and this represents the red line represents the delta US, and the green line represents delta UG, which are potential spring energy and potential gravitational energy. When this cancel, the kinetic energy, which is the blue line, is in the zero position, which means that the delta E must be zero, And as you can see through the whole graph, the only line that stays on the zero value all the time is delta E. And this means that the energy principle is satisfied. So in conclusion, it is possible to create a computational model that accurately depicts the movement of a spring. The fundamental principles are accurately used in order to describe the motion of the mass of the spring, such as the Newton's second law, and the energy principle, and also that the energy principle is satisfied by our choice of system. Thank you for watching.